Well, it is 9 a.m. sharp here, so I think maybe I'll start with a couple announcements. Good. This is just a slide that's added to the end of the welcome slides. So if you want to look at any of these points in more detail, feel free to open that up. But we just had 3 quick points that came out of reflection and discussion about yesterday. So one is we want to sort of gently rethink the full group discussions when we come back from the breakouts. There's been a lot of really great ideas and great discussion, but we want to try to keep discussion about individual topics somewhat short, since we have only 30 minutes roughly each block with the whole group. And we want to make sure that the discussion about a given topic is contiguous. So basically, if you're going to raise a point that's different from what's being discussed right now, maybe hang back or indicate in some way that you're going to change the topic. And then, of course, we want to encourage you to continue any of these discussion threads on Slack. And then a final point is, if you want to raise a question or raise a point and you don't feel comfortable doing it vocally, feel free. There's a new section in the Google Doc you can go to called Questions for Discussion. If you put something in there anonymously, I or one of the other SSD members will raise it in the discussion for you. Another thing is just some guidelines on the randomized breakout sessions. I think it would be good if we all do we have some structure to that. So start with very brief introductions, name, affiliation, what you're hoping to get out of the given day's discussion. Then as a group, try to identify a moderator or a facilitator. This doesn't have to be me or one of the other organizers or moderators. This can be anyone. And we encourage it to be someone who's not one of us. And if you are a moderator, we want everyone to have the opportunity to speak. So make sure junior people are given the opportunity to share, especially. And then the last point is quick. The labeled areas in WonderMe are not rigid. They're just suggestions. Don't feel like you have to go cluster in the theme for a given day. Make sure, split into subgroups and have informal discussions as you will. So that's it from my end. And now I'll pass it over to Alice and Mike to kick off day 2.
Here we are, starting up day 2, large-scale constraints on dark matter. This is just a brief introduction that Alice Deason and I will do. We're going to talk first in 2 parts. The first one is the main science questions. And then the second one is questions related to the measurement of large-scale properties. So I'll turn it over to Alice first here.
Thanks. And first of all, thanks for organizing. And I really enjoyed all the talks in this session, although thanks also for giving us the longest talks of the workshop in our little group. That was much appreciated, but they were all excellent. So what we thought we'd start with was what the main science questions are for this kind of large scale constraints. So a lot of the talks touched on, what is the mass, shape and concentration of the galactic potential, and why these are important. Can we put important constraints on dark matter models? And although this is more the topic of tomorrow, the small scale structure of dark matter, there are still important connections between these large scale constraints and what the small scale problems are. Okay, and so in terms of these main science questions, I think a lot of the talks which are highlighted here on this slide did, discuss either the mass or the shape or the profile in terms of the concentration of the galactic potential. And it's clear that this is one of the main aims that we want to do, something that with streams, there's a lot of potential to do. What was very clear from these talks, there's a lot of different ways to get the same measurements, and they can vary quite widely. So one thing as well, moving forward, and it was mentioned a lot yesterday, was how we get robust constraints in these quantities that we can actually with confidence say what they are and with what error bars. Okay, next slide, Mike. And then I think almost every talk, if they didn't mention it explicitly, mentioned the LMC, and the LMC is now what I like to think is like the equivalent in galactic science of magnetic fields. We now say, what about the LMC every time we do anything? So it's clear this is something we can't ignore anymore. And we're in terms of all these 3, mass, shape, and concentration, we need to consider the LMC. There are also talks discussing constraining properties of the LMC itself. And it's clear that moving forward in this field, we can no longer think of our galaxy as just, a galaxy on its own. We have to think of the full potential and this massive component as well. And I think that will probably be a very big topic of discussion moving forward. And Sagittarius, of course, I didn't mention Sagittarius, I've forgotten about it. But yeah, and Sagittarius matters as well. Okay, thanks. And then in terms of constraints and dark matter models, clearly, if we're going to measure these things, we have to convince ourselves and others why they're important to measure. Does this tell us anything about land CDM? Is there any point knowing the mass of the Milky Way to 1%? Should at some point we say, look, we know it, let's all just not do this anymore? And we should probably decide at what level we want to do that. Can we use these large scale constraints to tell us anything about dark matter models? Lambda CDM in itself is quite a difficult theory to disprove, but there are probably spaces that we can exclude from these sort of constraints on our galaxy. And this was touched on as well in some of these talks. And then again, this is more connected again to tomorrow, but I think it's important to remember that there are strong connections between these constraints and small scale or apparent small scale problems. And part of the reason we want to know these things is for this reason. So in terms of just basic things like how many satellites there should be, that really, these large scale things like the mass or even the concentration really matter. And then the stream structures, when we model streams, we need to know the galactic potential, etc. So there is a strong relation between these things, and in some way we can't decouple them that straightforwardly, and that was also discussed in some of the talks. Okay, now I'm handing over to Mike to talk about more technical things.
Yes, yeah, on the more technical side. I forgot to say it at the beginning that the very brief titles of the talks came from me. So if I didn't characterize your talk well, feel free to mention that and correct me on that. And also the way that the talks have been organized into these slides is not a definitive connection, but it's something that that we saw when we were going through them. So we'd of course be taking suggestions about where else to put those, what other connections to make. Okay, so talking about the question of accurately measuring the large scale properties or robustly measuring the large scale properties, we identified a few key questions, and then there will be some subpoints to these in the following slides. So the key questions here, we identified what are the pros and cons of physical or canonical space versus action angles. You probably saw a lot of talks about action angles. I think that Rodrigo Ibato's talk is a really nice introduction to the concept if you're unfamiliar with those, which people very well might be here. And then the second question here, how important are time dependence and non-equilibrium modeling? If you watched the talk that I gave, you know this is probably a leading question from me, but I'd like to talk about where it breaks down and where equilibrium modeling will give us good information. And then third, one of the key questions, given the messiness of realistic halos, the fact that we do see all of this substructure either in real data or in when we look deeper into simulations, do our methods work? And some talks really worked to address that as well. Okay, so on the first question, what are the pros and cons of physical canonical space versus action angles? And most people, most of the talks that we highlighted here really came down on the side of looking at action angles, and that's why I highlighted that or italicized it here. And then the corollary question to me is this question of where, when, or how does the assumption of equilibrium break down as a diagnostic utility? And then I highlighted a few of the talks here. Obviously, these talks all have fantastic results, and the question is how far can we push the limits in some of the discussion that's already been taking place on Slack sort of alludes to this. Again, if you look sort of in the machine learning identification from Rodrigo and asking questions about how we could probe the changing Milky Way potential over time, even still in the action angle formula, even though they're in the formal equilibrium interpretation. The second question here, how important are time dependence and non-equilibrium modeling? And then the key sub-question to me here, there's obviously room for much more here, but the question might be, what are the pros and cons of using streams as the primary diagnostic here? Of course, this is a conference all about streams. So the question is, how far can we push streams in terms of answering questions about the importance of time dependence or non-equilibrium modeling, or whether those are somewhat overkill. And there's a lot of talks that went under this, as Alice mentioned, largely alluding to the interloping of the Large Magellanic Cloud lately. Eugene had a great talk about Sagittarius as well, and some of the importance of non-equilibrium modeling there. And then lastly, this question about, given the messiness of realistic halos, the question, how successfully are we measuring what we actually think we're measuring? A variety of talks on this as well, some about stream recovery and cosmological simulations, and then some looking at the techniques related to mass clustering, or techniques for measuring mass related to mass clustering here, and constraints on the halo shape when you've taken them out of cosmological simulations and then tried to transfer that learning onto what we actually know about the Milky Way. So again, this is a summary slide of there are a lot of talks today, as Alice pointed out. We had quite a bit to talk about. We had quite a bit to cover. This is just a real teaser and really trying to connect the talks to the various large questions, which I know that we'll build on during the sessions today. So I'm looking forward to seeing what comes out of this. So I will actually stop sharing, unless Alice, did you have anything else to add before we go to small groups?
No, I think that was good.
All right, and I will stop sharing and we'll ask to be pushed out to our small groups.
Just to check, does anyone have anything they want to throw out very quickly? We have just a couple minutes here, or questions for the moderators. Good. Okay, well, hopefully that primes your brains, and we're going to send you out into breakout rooms again. Again, just a reminder to do some introductions, identify a facilitator or a moderator for your breakout room, and that doesn't have to be one of the organizers or one of the conference moderators, and make sure that you give everyone a chance to speak. So we're going to split out for about 25 minutes into random breakout rooms, and the conference moderators and organizers will try to go one per room. So we'll join in a minute once we see how things shake out. All right, we'll see you in a minute.
All right, so we have a half hour for discussion. I think, Alice, unless you had another thought, maybe we'll just push it back to everyone and ask what people would like to share.
Yeah, let's go through the rooms maybe in order. So I don't know how many there were, but we can start with room number 1, breakout room 1. Someone there wants to tell us something? No? No one in 1? Okay, 2?
No, I really want others to bring up, but
okay, go
I
for
don't
it,
want always the person to talk about. I really think we have something very good ideas to share, and so people can look more on the notes. But I want to highlight a few of those. So we discussed in terms of like what kind of stream, because we talk about the messiness of this when like considering LMC and the SAG. So there's question about like what kind of stream and how many stream do we need to disentangle this kind of messiness, and also will we encounter more messiness when we get better data, and maybe we need some cosmological simulations to help answer this, and also related to how precise the potential we wanted to measure. But I also like the thing that I think Thomas brought this up during this topic is can we learn the Milky potential with the data itself? It's more like a data-driven way with machine learning to answer this. So it's not like modeling multiple like halos with like throwing an LMC and throwing a Sagittarius to fit, but more like using the data, maybe using some simulations, training sample, but then like the data to help us to measure this messy potential. I think that's kind of interesting. And the other questions I think we have is like, can we do this potential fit with 4D only, so the proper motion and the position And if not, then when we say we need a radial velocities and distance, do we need a more like larger sample with lower precision or higher precision but smaller sample size? That's another question that we had. And I think another thing Eduardo brought up, and a lot of people second, is that we think that we are lack of access tools for simulating streams in a time-dependent potential. I think there is a lot of tool we can use if we're doing a fixed potential, but when we go into the time-dependent, especially for observers, we don't really have a good tool to, or user-friendly tool to use on that. And we hope the community can help. So yeah, so I'm just gonna summarize these 3 points I think I heard from our breakout room 1.
Okay, great. Is there anyone from room 2? No? Okay.
Yeah, I mean, I think we were
Go for it, Anna.
we're discussing along these lines, but I think I don't want to be the one to be reporting because yeah, I feel like we should share the air. So maybe Elise or Bertrand, would you want to give a few takeaway points from our discussion? Are we still here? Okay. So, case of cold feet, maybe. Okay, so maybe just tying into this, what Ting was mentioning, we had a little bit of a discussion of kind of how can we combine all of the data that is out there. There's just a lot of it, and people use their kind of favorite streams or favorite other tracers, and I feel like there is a need to for kind of single repository where that's kind of a value-added catalog that has all of the kind of Gaia measurements of individual stellar streams and maybe some other spectroscopic data, and the same for other tracers, not just streams. So this is like a second aspect that we were discussing. So in addition, kind of how can we improve the constraints on the global shape or matter distribution in the galaxy by using streams in concert with other tracers. There's also a little bit of a discussion, kind of the kinds of things we learn from studying the shape of the Milky Way in detail, and kind of how do we compare that to cosmological simulations, and what it means to, or kind of how serious the tensions are in the kind of cosmologically expected shapes of dark matter halos versus what we are finding in the Milky Way. So that was also an interesting kind of discussion that could be made around that point.
Okay, thanks, Anna. So that was, were you room 2 or room 3?
2.
Okay, so room 3.
I don't quite remember whether we were at room 3 or not.
You can just go anywhere, Eugene, if you want.
Okay, well, I'll go for it then. I think one thing that we just did discuss was the fact that, or the observation that you actually get better constraints on the potential when using multiple streams, unsurprisingly, than even knowing a single stream in exquisite detail doesn't help you much against, does not guard you against various sorts of degeneracy, because you're not probing enough range of radii. And also, not all streams are equally useful. Those which are spanning, those at pericenter or apocenter are actually not quite as useful as those that span a larger range of radii and phases in angles. Another thing that I think popped up was that, yeah, well, it is related that when using only a few streams, you are prone to overfitting, your potential could be very biased. And you could check the ways that you're fitting correctly or not by examining the radial phases of your debris. And I think another point was that related to non-equilibrium models, which we did not really have time to discuss properly. But there was a conjecture that the streams are perhaps less affected by the features in the real Milky Way that we have, rather than smooth hail component. So you're a bit more safe on the, if you're looking just at the streams to constrain the potential, even if the potential is not in equilibrium. But I think that needs to be studied kind of in more detail. Anything else there to add, guys?
Okay, thanks, Eugene. Oh, Adrian has his hand up.
I guess I had a question about that. Do you think we could like jump in and discuss some of the points? Is that cool?
Yes.
I was so you were bringing up the point that streams might be less sensitive to some of these issues, but I thought it was, the way I think of it is that they're more sensitive and therefore more informative about those things because they are phase coherent structures compared to, like, if you took a ensemble of tracers that we have to make some assumptions about their dynamical state, they're less informative about these things.
I would maybe rephrase what Eugene said as they're less susceptible to the biases that are inherent in assuming an equilibrium population and then trying to model it. Because when you model streams, you're fundamentally modeling a non-equilibrium part of the system. And so you're not quite as mismatched between your assumptions and the model and the actual situation. But I see what you mean about that. It's fair to say we need to do a little more work on that topic.
Sophia, go ahead.
Yeah, so I mean, I had a look at this, how actually streams are affected by passing through a deformed halo. And for example, like given the LMC and the streams in the northern part, for example, I had a quick look at GD1, there was no difference whether the LMC was deformed, even the Milky Way deformation up there didn't put any effect, but then streams which pass closely by are more affected, like Chernobyl, for example. And yeah, we also had a quick look at dwarf galaxies, how their orbits are affected in the non-deforming and the deforming potential from Milky Way and LMC, and they are way less affected than streams. So I guess most of the streams which are not passing close by the affected areas behind the LMC are not as affected. Yeah, well, streams which are close are affected. And I guess the same is for streams which had an interaction with Sagittarius and passed close by there.
Dennis?
I just wanted to echo the points that were just raised in terms of, yeah, like what's nice with, one thing that's nice with streams that I think perhaps going back to Adrian's point is that the streams have signatures which can't be reproduced in any kind of time independent potential. So for example, like some of the streams have misaligned proper motions where stars don't point along the stream. And that's like a signature that you have to put in something, you know, which is perturbing the stream. Or perhaps in the stellar halo, if you're in that part of the sky, maybe it wouldn't be quite as obvious that you have a severe problem with your model. So streams do kind of have telltale signs when you aren't fitting them right.
For the smooth halo, of course, the signature would be that your mean line of sight velocity is non-zero, for example.
Yes, I mean, I guess there are, yeah, sorry.
No, go ahead, Dennis. Go ahead, no, respond, and then I'll go to Catherine.
Yeah, I guess, I mean, Eugene is fair that there are signatures in the stellar halo as well, but I feel like with the streams, for example, it can be something that's kind of very, very apparent. Well, for example, with velocities in the stellar halo, it is conceivable that you could have, let's say, some long-lived sloshing from like an old accretion event that hasn't had time to phase mix yet. So there are other things which could mimic that. But again, I'm just saying that, yeah, I think that's a fair point that Eugene raised.
Catherine.
I think two things. Of course, I'm biased towards streams, but two things. One is they're not self-gravitating, so they're really tracers. And you can say the stellar halo is tracer, but you don't know its distribution exactly. Dennis's point, and this is really this is really come to play when I'm thinking about the disk. The disk is self-gravitating in a crazy way, but there are also phase mixing structures there. So the beauty of streams is it's really that you know their origin and their phase mixing structures, and so their tracer populations. So there's just fewer assumptions going into the interpretation. So I think I'm firmly on the side of streams being more sensitive.
I see that the three of you were all in room 8. Was there anything else from room 8 to report back on? Anything else you talked about?
We asked Sophia to give a full report, so I suggest you ask Sophia.
Go ahead, Sophia.
Yeah, should I just wait until it's our turn, or should I go?
No, go ahead, Sophia. We'll go out of order.
Okay, good. So we actually did not discuss this too much. We talked about quite a lot of other things. So we first talked about action and action clustering. So whether they are really completely constant or not, and how good they are at, how constrained they are along streams, and what happened if those streams had encounters with dwarf galaxies. So some people had some work that they were actually taking quite up some space in action space, so that they were not super constant, but also that like what you could learn from those changes of actions along the streams, or even jumps along the stream. But then we were also thinking that you always like need to include a potential, so that the actions depend on a potential, and that when we don't know the potential correct, do we know the actions well enough to infer this? And so maybe action finder could be like a way where we don't depend on the potential, to learn more about where actions are not very constant, or like where there are changes in actions along streams, what we can learn from that without needing to depending on the potential. And then we were also discussing the question on when do we know the halo precise enough, or whether we know it already. And we were all on the side that we want to know it better, and that there's a lot of things to understand from the halo. And so there's no limit in how well we understand the halo, the mass and the shape, and things within, such as like the wakes, the twisting, figure rotation, deformation, all these things. And it will also help to understand dark matter models. So comparing lambda CDM to self-interacting dark matter to fuzzy dark matter. So only when we know, when we measure the halo well enough, when we know the halo well enough, that we can learn about these very precise things, which ultimately help us identify the nature of dark matter. And then, we also obviously talked about deforming potentials and how great basis function expansions are to understand what's going on over time, and to understand simulations, but also data. And that's probably the next step away from axisymmetric static potentials, to understand changes as function of radius, changes in the shape as function of radius. In a non-parametric way.
We can continue to go out of order in rooms, or if someone's ready to jump in, otherwise we'll have room 4 go. It looks like there are lots of discussions though, so please raise your hand if you are going to report from your room. Or bring up a point that someone hasn't said. All right, Sukanya, go ahead.
Oh, I just meant I can report from my room, but I think I was in breakout room 9, so I can wait unless you want to go out of order.
Go for it. I'll keep track.
Okay. All right. So we talked about a number of things, but we sort of had 2, I guess, main questions. One is there knowledge of an equilibrium radius, a question brought up by Martin, within which we can more or less assume equilibrium. And another question is, what do we want to know in 5 to 10 years? What are the big questions that we're trying to answer in 5 to 10 years? So in terms of the first question, is there knowledge of an equilibrium radius? There were actually quite a few different views on this. I would say, from the work that we've done with pulsar timing, with direct acceleration measurements, we're starting to see some differences with more equilibrium approaches, even at small radii on the order of a kpc. So I found that somewhat surprising. And there could be, of course, the effect of the LMC on the outer halo with collective motions. And it's well known that SAG, with its multiple pericenter approaches, has influenced the disk. But we couldn't really come up on, so this is maybe an interesting question to think about. What is this equilibrium radius, if there is one? And the other question of, where do we want to be in 5 to 10 years? Rohan pointed out that we can now reconstruct the merger history, and maybe we want to think about incorporating the information that we have from the succession of mergers into how we think about the shape of the dark matter halo. With the EDR3 measurement, direct measurement of the solar acceleration, there's a really nice possibility to combine that going forwards, also with pulsar timing and high precision RV measurements to get direct accelerations, which I think would be really interesting to combine on these smaller scales with streams on larger scales. So that's a question that I'm really interested in hearing your thoughts on. We also have talked a little bit about there's interest in knowing the ages of globular clusters that have been discovered in SAG by Dante and others. I think also in terms of the question of, how do you know if you've expanded the potential correctly? That's I think another area where I think the direct acceleration measurements have can have significant impact in terms of, they don't assume equilibrium. So I'd be interested to know how the more traditional methods compare to that.
Great, thank you. Yeah, so I'm cognizant that we have about 10 minutes left. Other rooms that have things that haven't come up yet in conversation that want to report?
I can report room 7. Unfortunately, I was assigned that. Sorry.
Go for it.
So we discussed a lot about clumping in action space in particular. Why, when you see clumps in action space, how do we know that's a distinct progenitor? So we discussed that, particularly a massive progenitor, how it might have multiple clumps and how we can disentangle that when we're doing these, stream finding algorithms and things. We also discussed the testing these things like time dependence of actions and angles using cosmological simulations. So there's quite a lot of discussion how we need to use these tools to test some of the methods that we're using. Can chemistry, we haven't talked that much about, there's action angle space and dynamics and how chemistry fits into it. We also all thought distances were very important in all this stuff in action clustering. So RLI are ideal, but there's not many of them. And then we also touched on using more phase information and frequencies as well as just action angle space and how that might improve things. And yeah, I think that was it. Is there anyone else who was in that room who wants to say anything? No. Okay.
All right. The other rooms look plenty active too. So 4, 5, 6, 10. Anything that hasn't been talked about yet? Nathaniel, go ahead.
Hello, everyone. I was in group 5. I just want to touch on, I think one thing that we talked about that relates to a number of things that have been discussed before, that the action angle formalism and, its sensitivity to time dependence and perturbations to the LMC. These things, of course, depend on the location in the Milky Way, and that perhaps one of the things we need to think about is when looking at multiple streams, it may or may not be feasible to model everything in the same way, that the time dependencies and the sensitivities to things like resonances mean that we have to start treating different parts of the Milky Way differently, even if we apply the same potential for global properties like the total mass and stuff like that. So that's streams being such exquisite measures of the local acceleration may, in addition to being so useful, also be one of the many things that complicates how we get out bulk properties.
Cool, thank you. Just skimming through 4, 6, 10, anything that we haven't talked about, or also responses to anything that's been said so far? Sorry, Marius, go ahead.
So I'm not in one of those groups, but I just wanted to stress how important, because we talked about many different tools of actually being able to, recover the properties of the Milky Way. But ultimately, if we really want to trust those results, we should really try and test all these methods, like on simulations as closely as possible to what we think is the Milky Way, like with many of the complexities that we actually want. Because that's, in a way, it's like the ultimate test and how well can you actually trust, trust your results. So I think we shouldn't forget that one. So I know it also involves a lot of extra work, but ultimately it's also like one of the gold standards to be able to, to trust our results.
Are we sure that cosmological simulations are capturing all the physics that we need?
Probably not, but if you have anything better, I'm totally up for that. The idea is that you want to test it on something as complex as you can. And then
we just had a request for you to talk more about it, actually, so go ahead.
I don't know, just wanted to say that actually if the method works perfectly, in that case, of course, or maybe the reality is even more complex, but at least, given what we currently understand, at least you see why we don't get any biased results and so on. And maybe even more importantly, that the uncertainties that we actually estimate are realistic, because many times we use, simplification in our models, and all these simplifications can actually propagate in in many unwanted ways.
So Lachlan brought up a point in the chat. Do you want to share that, or?
Yeah, I was. Yeah, just all the talk about how useful actions can be and whether you can treat them as constant, and whether this may be a statement which is dependent on position in the galaxy. I was just thinking about how it relates to these efforts to sort of constrain the potential using clustering in action space. I guess the idea overall is that if you have many different things which are constraining, you have many different streams, you can't sort of over cluster anything, because you can't over cluster everything at the same time because you have tons of different constraints. But if you can't actually treat actions the same way in one part of the galaxy as the same part of the galaxy, how does that sort of assumption that you have tons of different constraints break down? That was sort of my.
I think that's a great question. I'd love to know more about that. There's a request for Adrian to make a thread related to his question. Adrian, did you want to bring that up, or do you want to take it to Slack?
This is a topic change, so I didn't want to derail. And if anyone wanted to respond to Lachlan.
So maybe I can ask for some clarification. Why can't we treat actions the same way in different parts of the galaxy?
So I think with regards to our breakout room, Dennis talked about this the most, but so maybe he wants to say something. But in general, sort of depending on where the largest perturbations are in the galaxy, sometimes you can treat actions according to some potential, in the northern hemisphere maybe, but not in the southern hemisphere because they've been more affected by that. See, I don't know if that's a good summary, Dennis.
Dennis, go ahead.
Hi, everyone. Yeah, I just wanted to kind of echo those points. I mean, so with actions, like there are parts of the, the Milky Way, there's kind of a nice picture developing with like Mike's work and Nico's work and some of my work, showing that some of the parts of the Milky Way respond adiabatically to the LMC. So like those parts, like in the inner Milky Way, probably have nice simple shifts in their actions. But in the outer Milky Way, there are parts that pass very close to the LMC. They're going to get extremely large perturbations. And their perturbations will depend on like their past trajectories. So it won't just be something simple. You have to be able to integrate things backwards, figure out where they were in the past, where they passed close to the LMC or not. And so I think it'll be quite, that can be done. I think we've got to figure out a way in order to encapsulate these different action changes throughout the Milky Way and how it depends on the past trajectory of each, star or each part of the stream. And we can do this for, simulations like with n-body simulations, but I don't know how it can be done within the action angle formalism. But I do echo Lachlan's point that I think we shouldn't try to treat different parts of the Milky Way differently. I think we should try to come up with a coherent framework which works for the entire Milky Way, because that's much safer, I think.
I agree with that. Mark Fartle asked about if we're worried about the LMC, should we also be worried about the SMC? Mark, did you want to say anything else about that, or are you just throwing that point out there? It's a worthwhile question. Amina,
I figured you're
Mark,
the expert. I figure you're the expert on this topic. I'm just throwing it out there.
Yeah, well, there's a reason I'm not talking about it. It's really hard. So I'll throw it to Amina. Go ahead.
Actually, I wanted to hear more about that point on the SMC, because I'm actually worried that when you model because the SMC and the LMC fell in together, right? So as a group. So when we just consider the effect of the LMC on its own, and we're forgetting, this 10% mass effect, will affect the trajectory, and therefore all the perturbations the LMC has on the streams, for example?
Yeah, I don't know. It's a good question about that. I think, speaking about the model that Sophia presented, I certainly wouldn't trust it in, interior to 20 kpc of the LMC, because there's not even a disk in it or anything right now. So that's a serious place for upgrade, and a spot to look for if there are implications for the large scale structure based on that. We have 1 minute left. So are there any concluding thoughts here before we go to a break? Alice, is there anything I forgot?
I don't think, Dennis, is your hand up or is it still up from earlier?
Oh, Dennis wants to comment on the SMC. Dennis, go ahead.
Hey everyone. So I guess I wanted to comment on that. So I think, there's a reason that we don't include the SMC, at least at kind of leading order, which we're trying right now. And that's because the SMC is heavily, heavily disrupting right now. It's like 15, 20 kiloparsecs along the line of sight. There's, kind of velocity dispersions look as if it's disrupting. So we think that the mass there right now is not that high. And so we have tried to, rewind the SMC and see what it does. And it affected almost nothing. There was only one dwarf galaxy it affected in terms of, like past trajectories of dwarf galaxies, and that was to Tucana 4. But everything else didn't change. For the streams, we have looked at, so like with Nora, we have tried putting in the SMC. I've done this as well, trying to see what happens, and it doesn't really affect the streams at all. I will say that, the dark matter of the SMC obviously is quite substantial. Probably it was, above 10 to the 10 in the beginning. And that stuff is orbiting the LMC right now because it's been disrupted. So I think our fits of the LMC are probably capturing the combined effect of the dark matter of the SMC, which is orbiting the LMC, as well as the LMC itself. So but right now we're still on the kind of leading order treatment of the LMC. But I think it's not a major effect to ignore the SMC for now. And like part of that also about Amina's point about the trajectory in the past is that most of the perturbations we're talking about happened quite recently. The LMC's pericenter is 50, 100 mega years ago. The perturbation with streams is within the last 300 or 400 mega years or so. So we think it's fairly reasonable given the SMC's present day light mass, but obviously it's a subtle point still.
Yes, I think worth considering. I want to throw back to the organizers to wrap here, or?
I guess, unless anyone else jumps in, I will say.
That's you, Adrian.
Well, there are other SOC members. Okay, so yeah, now we have a 30-minute break, so feel free to break out to Wonder Me. Let me get you a link here. Okay, no, I'm failing.
I can do it.
Maybe. Okay, thanks. Jason will put a link into the chat. So be back here in about 30 minutes, and we will, during the Wonder Me break, we will sort of collect some of these great ideas that have been brought up into 2 themes, and then we'll make the next set of breakout rooms specifically tailored to those themes. So we'll see you back here in 30 minutes.
So welcome back to everyone after deciding during the break what the 2 rooms are going to be. There's 2 breakout rooms. The first is titled Conceptual Aspects of Milky Way Modeling, and it's going to address questions like, what do we want to measure? What is shape? Are the models of the LMC, SMC, Milky Way, Sagittarius interaction complex enough? And are we missing important stuff? And then the second room is going to be titled Methods and Tools for Milky Way Modeling. What methods can handle equilibrium and disequilibrium, and what tools exist or are missing to enable this? So I think we're going to self-sort now and then reconvene it in 40 minutes, right? So join one of the breakout rooms. A little bit. Again, this room is built for the methods and tools for Milky Way modeling, trying to answer the questions like what methods can handle equilibrium and disequilibrium, and what tools exist or are missing. And just to kick off the conversation, during the break while we were organizing the groups, we were kind of talking about whether we want something like just being able to turn on Agama or Gala or Galpai and have a basic sort of fiducial model for the Milky Way LMC or Milky Way Sagittarius or something like that, and what the pros and cons of that might be. But I will stop talking and I will open the floor up to questions. Please feel free to raise your hand and I'll just start calling on people. Yeah, go ahead, Maris.
I'm not going to say anything super deep. I just want to say that ideally we want to have as many methods as possible, for modeling the Milky Way, such that in a way, if you can use that you can easily use. So maybe like, well, of course, or Fourier variables, such that you can try several ones and then get an idea of some of the systematics. Like when you apply one method or another.
So there's one proposal to build just a lot of different methods and compare the pros and cons of those responses.
Well, that's
to
what
that
we are constantly doing, right?
That's kind of where we're at right now, I think. Yeah. Is that a workable model for us?
Well, ultimately we'll have to go towards that, no?
Could you say a little bit more about what you mean?
Well, because so you don't want to have only one approach of studying the Milky Way system. And also when you have different probes, so maybe like one method is better than another one. So for example, for streams, I'm sure that because what you have is the orbit of the progenitors, and then you have the stream arc tracers along the same orbit, so you can get the acceleration quite well. Or maybe if you already have something that is highly phase mixed, like a stellar halo, then what you have to do is start from some distribution function, and then you need a different kind of modeling. And maybe more generally, so because at the moment we have already different constraints on the mass, the mass distribution in the Milky Way, no? So should we maybe try and make those Monte Carlo chains or something Fourier variable? Would people be interested about that? Such that you could easily go and maybe incorporate whenever you have, let's say you use a new stream and constraint, you can go and try and incorporate the prior constraints from some other analysis and see, like for example, how does it compare to the conditions overlap? Like if they overlap, how much better can you actually constrain when you combine with the data?
So something like a product where people can easily test their data constraints or their test constraints from their data.
Yeah, because for example, now already, if you look in cosmology, so there are already chains, for example, for the cosmological parameters that come from the CMB, and then you can use those, and for example, you could combine with analysis of like low redshift data, and then you can say, well, given my data, how much work better can I constrain? So similarly also in this case, that you could, on top of your paper where you present your constraints, you could also make your chains available. Even though it's always tricky because one of the problems can be that we all have different way of parameterizing the models. So that may be not easily to translate, from one set of constraints to another one. So yeah, that's one of the difficulties that actually arise, because maybe there isn't a natural choice.
Right. Yes, thank you. I forgot one thing to say. Can somebody please start taking notes, or maybe people already are taking notes and I just didn't notice, but if people could, if someone could do that, that would be great. Okay, there's a couple questions in the chat. There's a couple hands raised, so I'm going to try and circle around to all of these. So Nico, go ahead.
Yeah, so I just wanted to say that I think it would be important to see what kind of codes are available for example, for modelers and observers to use and test observations, for example, for running orbits, streams. And then if us could put our models on those codes so it's available to everyone. So in particular, I have thought about this and I say, okay, I want to put my simulation with the LMC on Adrian's code on Gala so everyone can iterate orbits. So I think that it would be nice if we can coordinate so we have different models and people can test, and in that way we can advance faster. I think that's my thought. So I don't know if there are other ideas or approaches that we should be discussing about that.
So you would be advocating for something like within the Gala framework, we work it so that multiple models can be plugged into that.
Yeah, or could be more frameworks, but what people like to use. I know that there are other packages, but it just that will be good for us to put the simulations there, so people can try them and test them.
Thanks. Sukanya?
Sorry, to unmute myself. So I know that people have compared the regions where equilibrium methods and genes, et cetera, fail for controlled simulations for the Sagittarius or really, like the Sagittarius interacting with the Milky Way, for example. Ellen Dongia, her student, did some work on this. And it was clear, this was using Chervin Laporte's SAG simulation. And it was clear that the differences for the actual true density in the simulation is increasing relative to what you infer from genes as you're going away from the galactic midplane. So I'm curious to ask if people have thought about doing this kind of comparison between essentially an equilibrium method versus, say, a real acceleration method in cosmological simulations.
Sorry, can you say what you mean about a real acceleration in cosmological simulations?
So, in any simulation, you have, you can measure your acceleration, right? That's very straightforward to do. So given that, or you can measure your density. And so, Elena and her student in their paper, I guess it was some time ago, a couple of years ago, they compared the genes estimate of the density as a function of vertical height and azimuth in Chervin Laporte's SAG simulation. And they showed how that, how it varies with azimuth and vertical height relative to the true density in that simulation. And the differences increase generally with vertical height. It depends where you are in azimuth. And so that's not entirely unexpected. But that is a controlled simulation. So I was wondering what might be the case if you look at cosmological simulations and do this for the acceleration directly rather than density or even just the density. That's really matter.
Right. So that's talking about methods to ensure that you're actually measuring what you think you're measuring.
Yeah.
Okay. Yeah, I think that's a great point. I'm going to keep moving on, and then please people raise your hands as you come back to these points. Jorge.
So 2 points. The first one regarding Mario's comment. I think we are all aware that every method makes assumptions, and some methods are going to suffer from those assumptions being very poor. Every method is different, but every And the problem here is that whenever you use a method, you have to adopt a method and make those assumptions. Then your result might be biased. So that makes it very difficult to combine, constraints from different methods. If one of, some of them might be more biased than the others. And the second point to Sukanya is that, I never know what to do with cosmological simulations, because we know that the configuration we live now in the Milky Way is extremely rare. I think Marius showed that in one of his papers, that the LMC where it is in the Milky Way, how it is, is perhaps a very small percentage of a typical galaxy in the universe. So, you might find that with some normal galaxies, a method works very well, but for this particular rare configuration, that method fails. So the comparison with cosmology, with cosmological simulations, I don't know how to put a value to that, honestly. I think personally, I would prefer to use constraint simulations, because at least we know we are as close as possible to the configuration we see, right? And not about imaginary configurations we could have been in those simulations. That's all.
That's a great point. I second all of that. I think, Simon, are you responding to that, or?
In a bit, or expanding, or coming a bit from another field, what has
Can I
shown...
pause for sorry, Simon, can I pause for just a second and get Marius's immediate response, and then I'll come right back to you. Okay, sorry, Marius, go ahead. Oh, you're above me.
Yeah, so I understand your worries, but ultimately we want to combine different measurements. So I think this is really what we should be aiming towards. So maybe we are not yet here, and that's the case. And secondly, I totally agree with you that what we really want, at least at the moment, why we cannot really get the Milky Way in a cosmological setting, we want to have constraint simulations. But even those have some assumptions. So ideally, we want to really go for cosmological simulations. And I know there are people working on trying to basically realize constrained Milky Ways in a cosmological setting, but it is difficult.
Yes, Simon, thank you for waiting.
No problem, thanks. Coming a bit from another field that also faces challenges with assumptions, modeling, and complex data. One thing that was very fruitful is we started blind modeling challenges in rungs of different complexity, such that also like new people can join. The first problems are very simple, a lot of methods solved.
I think that's Simon, right?
Yeah.
Okay, all right. All right, we'll hold Simon's spot in line to talk again, but in the interest of working through technical stuff, I'm going to move to Guillaume.
Yeah, so I had a question about also how we can model efficiently the different streams all together, especially for a lot of them that doesn't have any progenitors. Because the idea will be to get a full model of the galactic potential using all the streams available on the market, for which we have all the data, and with the new upcoming data we'll be able to do this model. However, we still have the challenging with the progenitor-less streams to be able to really get a final point to be able to start the simulation from. And I was wondering if a few of you have some ideas about that.
The question of progenitor versus progenitorless and getting ICs. Okay, we'll take some responses to that. I think, Simon, is your internet back? Are you here right now? Go ahead.
I hope so, yeah. So I think I dropped out of when mentioning blind modeling challenges. So there can be different learnings being done. So one also that we did that was in a strong lensing field is that we actually need good simulations. And there you immediately see where drawbacks are when you actually apply the methodologies on the data blindly. It's also a great learning for everyone that participated learned something. It was not like, it was not a challenge who was best or so on. So there were multiple metrics and many of the methods performed well in certain metrics and less so in others as expected. And this can be. I had a very good feeling in participating in those, and so it's challenging setting up, and it's a challenging participating because it takes time away from actually doing the analysis on the data, and so it may also be a challenge to organize a community that way.
I like that as a community resource. You were asked to elaborate on that, but I think we'll take that maybe to that larger conversation to Slack or the later days. I'm cognizant of not pushing everything to day 5, but keeping that in mind. I'm gonna hear some other voices, so let's go to Rodrigo.
Yeah, hi. So I just wanted to sort of bounce off of Guillaume's point, and I think it's been mentioned a couple of times now, right? So the progenitorless objects. And there I was just wondering if people had any worries other than sort of the subtle ones where, you know, we don't know where the center of the stream is just simply because we're missing it due to incompleteness. Is that the issue, or is there something more profound than that? Because otherwise one presumably could model it and then find where the center would have been otherwise, right?
Guillaume respond to that, or maybe Eduardo's responding to that?
Yeah, on that point, for Rodrigo, I think we also worry about what types of objects actually disrupted. For instance, if you put a normal globular cluster in GD1's orbit, it will probably not fully dissolve in the time to produce the length of the stream we observe, right? So I think, yeah, do we truly understand what was the population of progenitors that produced the streams we see today, and what causes some discrepancies that we observe in the progenitorless properties and the current globular cluster population? So I think in that sense, I worry about it.
Can I ask if that effort exists within current modeling frameworks, or do we need something new to build on that to enable this? To either Rodrigo or Eduardo or Guillaume.
Yeah, so so for the moment, with at least all the tools that I know, you still to get a terminal point. One of the ideas that we can have will be to spray particle along different orbits. So in that case, you don't really care about the progenitors. If again, you just are interested about the large scale dynamic, for other things, for sure, you need to know where is the progenitors. So again, it's really depending, but that's true that for the moment, we still to have a problem with, for my opinion, with progenitor-less things, because depending of where you put where should be the position of the progenitors, you have different answer about the morphology of the stream with different orbits, without speaking also with any other perturbation or things like that.
Mark.
So I was going to say that with regard to the progenitorless ones, it can be enormously helpful to know kind of the history of the object in terms of getting, you know, if you want to get the Milky Way potential constraints right. It helps to know how long the stars have been orbiting, and the stuff that Rodrigo has been doing with, you know, trying to look at the fine structure of globular cluster streams, you know, so that you can see it essentially bursts from different pericentric passages. I think that's going to be enormously powerful if we can do it, but it's also extremely hard. So I don't know what the method of choice is for detecting that sort of, like, you know, bursts of emission, but if you can do it, so it might be precise distances, or it might be like super precise velocities, you know, probably not proper motions with current levels of precision. But if you can do it, then you can tie down, oh, this is, you know, this is how long these stars have been going, and this is how long these stars have been going. And it gives you a much like greater degree of precision, I think, on the problem.
Do you view that as a large, I mean, what scale of problem do we view that as? I'm not saying that's inappropriate, I'm just wondering.
You mean, is it a stump? I'm not sure what your question is. Are you saying it's like it's a detail, or?
Yeah, I'm wondering if it's a small scale constraint on the structure that's happening, or if it fits in the large, how it fits in the large scale constraint.
I guess I'm still not really really sure. By large scale, do you mean large scale potential and small scale structures, or are you saying it's a big issue versus little issue?
No, large scale potential structure versus small scale potential structure.
Yeah. No, I'm saying that it's has to do with the large scale potential structure. And the thing is that these fine structures have been in the past difficult to distinguish from small scale interactions, like dark matter, subhalos, or maybe like also affect the bar, or just like maybe it's just some kind of like random Poisson noise, or problems with your observation or whatever. So figuring out what the actual structure of the tidal stream is and what it's from has been very difficult in the past, but there are signs that it's becoming a problem that we can actually solve. And once you do get fine structure of this of the stream, that's due to like the orbital properties of the stream, and not some little thing coming by and perturbing it, which is also in itself an enormously interesting question. But it would be great to be able to separate these things.
I agree, and if people haven't watched Tomer's talk, I want to just mention that Tomer's got a really interesting talk on that, something related to that. Sukanya, please. Thank you for
yeah, so I wanted to just address Jorge's point from some time ago in the conversation. Jorge, you probably know that I do tend to focus on control simulations, because I like that you can understand the physics as you're putting in one ingredient at a time. I guess I started thinking about this potential comparison to cosmological simulations for the accelerations and also the densities as inferred from genes, because we, when we compared the galactic parameters that we got from direct acceleration measurements and pulsar timing, even relatively nearby the sun, I think we see some discrepancies. So, one possibility is to look at, cosmological simulations. Another possibility is to think outside of the CDM construct as well, to understand what that discrepancy is due to. But the error bars are still pretty large, so, it may not be really statistically significant.
So I'm thinking about coming back to this, the overarching questions in the room, thinking about methods and tools for Milky Way modeling. We've kind of talked about, we haven't really talked about any of the like mechanical stuff. I'm wondering if there's input on that, but I'll go to Maris. Maybe it's on that or not. Go ahead.
Maybe a bit. So one of the questions that I want to put out there is that in principle, so we can increase the complexity of our model a lot, yeah. But then basically it would be very difficult to get any meaningful constraints from the data. So do you have any ideas? What's the best way to approach that, or when is complex enough?
What do you mean? Can you expand on that a little bit more, like comparing with the data?
The Milky Way halos using the basis field expansion. Yeah. In principle, you can take, I don't know, like 1,000 orders or whatever, yeah. And potentially the data is not good enough to constrain all of them. So is that the best way forward? Should we just maybe try some simpler models, but then in a way, let's say more physically motivated in the sense, and then we could maybe rule out some theories or theoretical models and so on?
Yeah, I mean, I have my own opinions on that, and actually and Dennis and I were talking about this in Slack a little bit about using, trying to identify model interactions or modes that are typical in simulations, and then modeling those specifically and trying to constrain observables using that. Jorge and I, just to plug our own work, had a really simple ideal for this, for the reflex motion, measuring the reflex motion, but you could easily imagine expanding on that. There was a related question actually about basis field expansions from Rafa. Can I call on you, Rafa, to do this?
Sure, it was very basic. I actually wanted just to ask how in computation time they compare against n-body calculations. The question being, if we want to see what tiny subclumps like 10 to the 6 solar masses would do to the Milky Way disk, the number of orders we need to expand the potential in, does it still bring any computational advantage over a pure n-body? Can we do controlled simulations with basis function expansions? That's the question.
Well, you can do an n-body in a potential that is expanded out in basis function expansions, right? So the basis function expansion just gives you an expression for your potential. And it's just a way of expanding it out that doesn't require you to have any sort of parametric reliance on the shape of it. So you're not saying, give me an exponential disk in a spherical halo. You're letting the basis function expansion choose that from the data. And then you use that as your potential in an n-body. So an n-body is related within that approach. It's just the basis function expansion is a way of choosing your potential.
But the question is whether you still can include substructure at the level of 10 to 6 solar masses. I think that was Rafa's question.
Well, but that's just the resolution of your n-body. I mean, you'd have to expand out a basis function expansion super far if you were expecting to get a potential that was that fine. But at that point, you're overfitting your potential. I'm assuming we don't have data that accurate. But you can make an n-body as fine as you want, as long as you're okay with the computation time being long for that. And that doesn't have anything to do with the basis function expansion. I would imagine that your potential evaluation is linear in time.
So I'm going to gently push back on how hard it would be to do that, and just say that I think we need technological upgrades, Rafa, to be able to do that, because since you can linearly add forces, there's nothing stopping you from having a giant potential for your Milky Way that's really simple, and having a nested highly resolved area in that potential that gives you self-gravity as well. So I think one of the next generations of simulations that we should be looking at would be something like basis functions, where you have a background large potential that's parametrically evolving or freely evolving. And then within that, you have something like n-body 6 strapped on top of it, so that you can follow globular clusters, or nested like substructures that you're following with their own basis function expansions that represent these 1 to 10 to the 6 mass systems that you're talking about. That would be my take on it, but no one's fully proven that you can do that yet. So there is some work to be done on that front. Please raise your hand if you obviously have any response to that. I want to push, there's stuff. Whoa, there's a bunch of stuff in the chat. I'm going to go to Mark and I'm going to read these and then we'll go from there. Go ahead, Mark. You are still muted right now.
Sorry. In terms of providing a potential for people, let's just think on how much mileage that people have gotten out of Joe Bovey's GalPi Milky Way potential 2014 model, and then taking one aspect of it and tweaking it. I mean, there have been many, many papers that have done that, right? Yeah, I think in the interest of people being able to compare their results, it would be great to do things as much as possible in a compatible physical model. If you want to like combine constraints from different objects and that sort of thing, or make any kind of inference, joint inference. And there's a big incentive to make things as simple as possible, even if they're not exactly the full accuracy. So, I mean, I think when people do, come up with some, you've done some project, you've incorporated some physical effect. I think you should think, how can I provide this to the community in the simplest and most efficient possible way, where people will actually use it, even if it's not quite the way I would use it in my own work.
Yeah, I think the question of the Milky Way potential 14 or the Galad type framework is really interesting, and something that we should really be discussing as a group. And I think this is sort of what sort of what Nico's point was getting to, being able to test different models, and whether a community project could be something like a fiducial Milky Way LMC model is a really interesting question. Somebody asked a comment when we were signing up for this, asking whether Eugene's Sagittarius is the last Sagittarius model that we're ever need to run, and whether we're done with Sagittarius now. And building on that, I think it'd be interesting to have a way to. I know Eugene I think you published the multiple functions, right, for your.
Exactly, yeah. So for the Sagittarius itself, it's fine, but the multiple functions are for the Milky Way plus LMC potential, which is exactly what you're after. If you forget and put aside the Sagittarius and try to use the same time-dependent potential for fitting other streams, that's exactly what it is for. And I think this kind of effort, it would be.
Right, so can I just ask, in principle, what you're suggesting is that within the Agama framework, right, because you can just plug your multiple expansions into Agama, and then you could run things in the time evolving Milky Way LMC.
Right, yes, right, yes. Yeah. You can compute orbits or make streams and so on, yes.
Right. So I'm not sure how widely known that is, because maybe that would help help preclude some of these conversations. And of course, we in the spirit of fully duplicating effort, like Dennis and Sophia and I have that same sort of thing available as well. So the question of how we can maybe work on these together might be interesting. Right, follow-up points on that. We have, it looks like 8 more minutes before we go back, or new conversation topics people would like to throw out. So can we go back maybe to the question of what we want to learn from cosmological simulations, and in terms of methods and tools? Is there something that, I think the split between trying to analyze cosmological simulations, and we had some talks on that today, and the question of running constrained simulations, can people think of pros and cons to both? Because right now it sounded like we were kind of sitting at a place where we feel like everyone in this room seemed to focus on running constrained simulations. Is there another point to be made? Marius, go ahead.
So maybe I'm misunderstanding, but I think when we run constrained simulations, we always start from some equilibrium state, which clearly will never be the case like in a cosmological setting. So I think that's one of the main disadvantages of constrained simulations. But I think maybe, at least at the moment, this is still maybe not dominant compared to what would be one of the main disadvantages of the cosmological simulation, which is very difficult to actually reproduce something similar to the Milky Way, simply because it's just one possible realization out of a very large parameter space.
Follow-up thoughts, Guillaume, first, and then Eugene.
Yeah, so it was to respond directly to Marius. Actually, when you do the cosmological simulation, you don't include any globular clusters or very low mass dwarf galaxies, which are most of the streams that we have been discovered right now. It is really hard to be able to observe it and to compare with real observables. Like when you want to get observable or radial velocities per motion of a few stars appearing in cosmological simulation, it's really hard to conserve the phase space of the structures along the time, because just you don't have the resolution of that. So you need to rerun that. So for me, that's also the cosmological simulation in that sense is also underused to be able to compare, especially for the streams.
So if I may say, yeah, so I agree with you that there are some other limitations. It's also the fact that we have limited resolution. So for example, when it comes to streams, not only that we don't find the galaxies, but even if you have the streams, can also be affected by numerical effects. So for example, Jobovi had a paper about that recently, that if you follow streams in live embodied simulations, and you get much more noisiness in the stream than you should normally find in an ideal potential. So all this we have to remember when we actually test. We have to keep in mind.
Eugene, I think you had a response to this.
Yeah, well, actually, 2 points here. One about the constraint simulations. I think the work that Andrew Ponson is doing for many years now is trying to make these, to marry the benefits of both approaches, make tunable simulations, which are set up in cosmology, but they are tuned to reproduce a particular property of the galaxy. So you probably should be thinking more about, can we borrow from those techniques to reproduce the Milky Way plus LMC system in more detail, for example. And the other thing about the streams in the cosmological context, I think that's exactly where basis functions could be helpful. You take your favorite cosmological simulation, you represent it as a time-evolving basis set expansion, and then you put in streams and you evolve them with a much higher resolution, whatever you want.
I have a follow-up thought on that, but I'll go to Nico first, and then I'll say something.
Yeah, on that note, I wanted to say about that. Cosmological simulations could be also very useful to tell us what processes are very important. For example, a massive satellite, triaxiality, the environment, and then with that in mind, we can focus on constraint simulations. What should we think about it? Like, for example, the presence of M31 that is nearby, is that important, right? It's more important than the LMC. So I think that using both is really important. So not that using one instead of the other one, but I think that having information from both is really powerful.
I agree. So just to note to everyone, hopefully you just saw the 5-minute warning. My only fear about expanding cosmological simulations and basis functions is a question that Charlie Conroy asked me in our small group session before, which is, it's not clear to me that you can guarantee that you've recovered all of the dynamics in this that you had when you were running the n-body simulation. If you do something like run the simulation in Gadget and then you expand, it's not clear to me that you can prove that you've recovered exactly the same dynamical modes. So, I mean, I think you probably can, but people will have to test to show that if you run a simulation with the basis function expansions that you've expanded, that you're going to end up in the same end state that you ended up with when you ran Gadget before, or something like that. Go ahead.
No, I was thinking about different things. You run your original Gadget simulation, and then you represent the time-dependent potential of that simulation by basis functions. You don't rerun that simulation, but then you can use that time-dependent potential to evolve your streams, for example.
Yes, no, I follow you, but I'm not sure that the basis functions that you've expanded that run through time, that if you start that with all the same particles that you had with Gadget, that you'll end up with the same end result. Meaning, are you sure that you've mapped the dynamics through the whole time accurately? So I think there's a lot of testing to be done there to show
that could be tested. In particular, Jason had a paper last year where we did test this in some limited context. Yeah, so that should be tested more.
But one orbit at a 2% level is different than a million orbits that all are at 2% level. That making sure that you've recovered the dynamics at the end is my only point. I'm just not sure yet. Sorry, that was a very technical aside. We have just a couple minutes left. Are there other open questions that people would like to make sure they get in this that we can bring back to the large group? Okay, I want to thank the people for taking notes. I hope that somebody will be willing to sort of throw out some ideas that came up during this conversation. I have not been able to keep track of everything that's been typed. So is there anything that we want to make sure that we bring back to the large group? Well, okay, there's conversations happening in the chat too. This is great, but hard to keep track of what's going on. Okay, so I think my summary would be that we have a lot of, we have multiple methods that we haven't converged on, but we might like to try to actually converge to methods where we can do something like a code test. Is that a fair assessment? Okay. And then we'll expand from there and see what happens in the large room. Yeah, Rodrigo, if you have a last minute thought, go ahead.
And it's just related to that code test issue, right? I mean, what worries me here is that we don't have anything we don't have any ground truth anywhere, right? And so all of the methods that we're talking about will probably have biases due to resolution, due to just the way in which they're set up. I mean, and just all limitation of the number of multipoles that you allow, et cetera, or just the way in which these, you could imagine a multipole simulation like that, just sort of, I presume it would have to be done at various slices in time, and you can imagine all sorts of weird effects happening as you switch between the different time steps of the potential, right? And so I just worry a little bit that we might do this process. And so I think this was extremely useful for the Gaia challenge and showing that, for instance, with, in the case of the dwarf galaxies, that you recover the right mass distributions. That was really a wonderful piece of work. But I just worry that in this particular case of streams, it might be very, very hard to actually know, to have an interesting case that would tell us what the truth really is.
Yes, I don't have much to say to follow that up other than yes, I think you're right. All right, so that's the end of the breakout room. We'll see everyone back in the big session. Please feel free to raise your hand in there and bring any of these points to the floor so we can continue to discuss.
Okay, so this room is talking about conceptual aspects of Milky Way modeling, which might first be good to define what that means, because I'm not exactly sure what that means. But the idea is the other room is talking more about the methods and the modeling aspects. I think we're talking more about what actually are we trying to learn from these measurements, like when we measure the mass of the Milky Way or its shape, what's the science goal here? I know it's a bit preaching to the choir because we all work on galactic-esque things, but it's always good to remember why you're doing what you're doing. So, and I should say, because this is a fairly large group, please just use the raise hand if you want to say anything at any point, and I'll keep an eye out on that. Does anyone want to start off with a discussion topic, something that's left over from the previous discussions or from the smaller breakouts or over coffee? Anyone? No? Okay, Sarah, thank you.
Yeah, I can just start a little bit about something we discussed yesterday, which is just the point that obviously the potential can vary in shape at different distances. And I guess I come back to the question of, it'll be cool to know how that transitions for the Milky Way. And there's been work on that. There were some of the talks yesterday. But to go from there to then generalize to cosmological simulations, I always kind of get stuck on what do we learn from this one galaxy, right? And the one shape. So it'd be cool to see that the Milky Way behaves in its transition and shape as the other cosmological simulations. But yeah, this was just kind of left over from yesterday. I don't have a specific question for everyone, but that's something I've been thinking a little bit about.
Dependent basis function expansion of the potential to make an accurate comparison.
Yeah, and in regards to the shape, so I was quite struck with the talks on this topic where, the disparity with land CDM, apparent disparity, like that some measurements were found, and then as a function of distance, there's also, there's been some recent work showing that there's a twist in the shape, which may actually be unusual for the Milky Way, which goes back to the question of, is that when we look at the shape of our galaxy, what does this tell us about cosmology at all if we're a bit strange, which I guess is always part of the problem when we look at the Milky Way. Sorry, Dennis, did you have your hand up?
Hi, everyone. It may be kind of windy where I am because I'm outside right now. But yeah, I guess one thing I wanted to raise in terms of the conceptual framework is, I think we should be thinking about putting streams in the cosmological simulations to test what we're actually measuring in these realistic contexts, to see what our answers for the Milky Way mean. Like we have all these results now for the Milky Way, like these strange shapes, for the inner halo. But then like Kohei's talk shows that by the same method within cosmological simulation, you actually get a bias there as well. Sorry, that's my son. So I guess I want to make the point that I think for each of the questions we're thinking about, we need to know how well does it actually work in a realistic framework. So I think we should be really testing our methods carefully in order to understand these limitations. And that applies for all techniques like streams, stellar halo. And I guess Alice has done a lot of good work on this already to test this kind of approach.
So Adrian, you had your hand up.
Yeah, I'd like to emphasize or plus one that from Dennis. I think something that I brought up with a separate group is just the thought that in terms of comparing the shapes of halos in simulations to what we're measuring from the Milky Way, often in the simulations, we take a snapshot or a set of snapshots and we compute the shape at a set of discrete snapshots. But we don't actually know, like Dennis was just saying, what we're measuring when we fit a model that has some flexible shape using a stream or a set of streams. We don't know if we're measuring the shape, like the average shape over time or the shape at some particular time. And there's, we've answered various things that are related to that, but I don't think we know that question.
Yeah. So Sarah, you also had your hand up.
Yeah, just related back to what you said, Alice, about the twist. So it confused me a bit to think that that was unexpected, because I've always thought that even in dark matter only simulations, we could actually have changing shapes of the dark matter potential depending on wherever something fell in the evolving accretion history. But I don't know if people disagree with that or found that surprising.
Yeah, I think you're right. There's quite a variety. I think the surprise was more how strong the shift was. I mean, not just like a small twist. It was, going from aligned, with the disk, but completely flipped in the outer halo. But there is also, this links back to, I think, the LMC and having like a late massive accretion event and the impact of the LMC on the shape in some sense, right? Because it, depending on the method of how you measure the shape, that is a big thing that can change it in the outer parts. So, but I think that it's a good point about what is expected and unexpected from the simulation, because sometimes I don't think that's clear until it's looked at. That's a good point. Okay, Alex, you have your hand up.
Yeah, I kind of wanted to double back to Dennis's point about comparing and our methods, like basically just using cosmological simulations. How much does it matter what type of simulation you use? Is it more important to have hydrodynamics, or is it more important to have an LMC in the right place at the right time? What's what criteria do we want to use for, okay, this is a good test of our method?
Okay, there's a couple who can't raise their hands. I'm not quite sure. So you can clap instead, I think. So Anna, are you clapping?
Yes, I'm raising my hands by clapping.
Okay, well, if you've got your video on, you do put your hand up. I'll also try look.
Yes. Oh, is it my turn?
Yeah, go for it. Okay.
Yeah, I was, I guess, also responding to a different aspect of what Dennis was saying of sort of putting, wanted to bring that up for further discussion of putting streams into hydro simulations, and actually I think I saw, well, Ozzy is here and Alice is also here. So I wanted to hear from people who have experience with like the more realistic mocks, and kind of what would it take to introduce streams in Ananke or Igaia, and I mean kind of globular cluster streams, and sort of. And I guess I can tier this, first just put them kind of for identification purposes, and then second try to evolve them simultaneously in that potential. So I would like to, anyway, if someone can talk more about that.
Azzy, do you want to? I'm not sure if that's why you raised your hand, but
yeah, actually it was related to the same thing. Actually, I was going to say now that Anna is also asked about that. I think there is one aspect is that in at least the hydro simulations, of course, we do not resolve anything like globular clusters, let alone having like a stream of whatever individual stars that a globular clusters form. So that's, to me, it's a little bit out of the question for the very near future. Then the next question is, I guess, in order to test some of the methods, can we maybe some sort of a semi-empirical way inject a global clusters that gets disrupted in some sort of a potential that's evolving? Something that maybe more people here know more about this is actually Joe Bowie. We had him a few weeks ago in our department giving a talk. He was showing us that actually the fact that in cosmological simulations, of course, we have limited resolution. Just because of the fact that we basically we sample the mass distribution in a discrete way because of the particles we have, that can change the dynamics of the streams quite a lot compared to in a kind of a realistic way where this resolution would be, depending on the dark matter type, could be very low. So that's, I think, a big concern, or not concern, something we have to take care of, and it won't be very easy, especially in a, let's say you want to have a sample of cosmological simulations with such a resolution that's perhaps relevant for streams. I'm a little bit on the kind of a skeptical, not skeptical, but cautious side.
I'm sorry, could you say that again?
Which bit? I talked for too long. So if it was related to the last part and the resolution, it's the fact that we have the Milky Way dark matter halo, or whatever potential it is sampled in a kind of within a resolution limited way. In the jargon of the simulations, we have mass of the dark matter particles, which in this case, even in the best cosmological simulations, these are by best, I mean highest resolution. These are at best 10 to the 3, 10 to the 4 solar mass per particle. So we're just basically sampling the mass distribution and not in a smooth way, in a discrete way. And that kind of extra noise. So these particles can interact with the streams, and these particles are kind of numerical. They are there to represent the mass. They are not real objects there, and one has to be worried about those.
So Robin, you've got your hand up.
Hi, I had a couple of comments. Going back to what Alex was saying about whether we need hydro to test modeling strategies, I think the biggest influence that the hydro has shown to have in cosmological simulations of this type has actually been just the extra deepening and contraction of the potential according to the formation of the galaxy in the center, because the baryons can lose energy more effectively than dark matter. And there are a few groups that have sort of intermediate things where they like grow a disk in the center analytically, plus the dark matter that can sort of speed this up with parameter exploration. Alex knows about these. But because one of them is there at Texas. But what was I going to say? Right. So then beyond that, I think, so it depends on what kind of tests you want to do to some extent. The other thing I would say on the side of how do we put lower mass streams into cosmological simulations, I think the problem isn't of numerical noise isn't quite as bad as it might sound from what Ozzy said, in my opinion, because most simulators use a softening length. And so if that is larger than the like typical size of your stream, you're not going to see quite as hard of kicks from individual dark matter particles. But I agree that it's a problem in a larger sense, in the case, just in terms of whether we've got the dynamics of the dark matter close enough to write, given that we're simulating a collisionless fluid with particles. So that's, but if you table that, you can also sort of look for intermediate strategies. We've been trying to see whether we can sufficiently model the cosmological potentials with a basis expansion well enough to reproduce the orbits of particles, which is the thing you'd want to do for streams. And we're getting some mixed results. I know that, Eugene and Dennis had a paper on this that they probably want to talk about in non-hydro recently, but in a hydro, it becomes a little more complicated for a number of reasons, some of which are relevant, some are not. So that's my like 5 cents on those topics.
Okay. I'm sorry if I butcher your name. Niashi? Sorry.
Oh, that's okay, no problem, Niash. I don't know if someone was before me, but I think I was just it's a response to some question I think came up earlier. That I mean, is Milky Way just one galaxy? It's not. It's not necessarily the typical galaxy. And I think two things that came to my mind, which is this question of, is solar system a typical planetary system? And that's something that, of course, I mean, until 20 years ago, we didn't really know much about. Now we know much more. And I'm guessing the answer is not clear to that question. We certainly know many planetary systems that are very different from solar system. So, so I think it's kind of drawing questions, answers about typicality of the Milky Way could be as complicated. And the other thing is, of course, we live in the Milky Way, so there could be some anthropic selection that some galaxies may not be as hospitable to life as others. So I know these are kind of maybe too conceptual of a questions, but I thought that maybe they're at the bottom, that I put that's probably the most conceptual question there is. You can ask in this group. Anyway.
Okay, thanks. So sorry, Dennis, I missed your hand.
No worries. I was just making sure that my hand was raised. I guess just about the questions about, I guess Alex asked a long time ago and Robin answered about, do we need hydro? I think the answer to that is yes, because as Robin said, having the baryons in there contracts the dark matter halo and makes the inner dark matter halo much more spherical than it looks within a pure dark matter only simulation. So we definitely need the hydro to get the kind of shapes right, because that will then affect, for example, how crazy the orbits look in those potentials. So like the kind of work that I think Tomar was showing, I think I'm saying his name wrong, but yeah, kind of with the resonances and stuff, that kind of resonance structure will be very different if you have a very traxal halo in a part versus a more axisymmetric and flat and spherical halo. There has been worked on like by Jason Sanders recently, doing basis function expansions to dark matter only simulations. And we are working on doing that on hydro plus cosmological simulations now in order to have fairly realistic potentials that do have that kind of shape correct. So I think disrupting and then fitting streams within that kind of framework would really teach us, what we're measuring, and that will like get around the kind of problems in terms of the kind of resolution of these simulations. I'm not 100% sure. I mean, the work by Neil and Joe on the effective resolution on streams was done for globular cluster streams. I think we can definitely probably try to look at, streams within cosmological simulations for dwarf galaxies, because those will be, since they're much hotter streams, they won't be affected as much by the dark matter substructure. I think we can do a lot of work with testing there. And in the same vein, we're also planning on kind of testing within, simulations of the Milky Way and LMC disrupting around each other and seeing what streams look like in those simulations and how fits to those simulations look and what they're actually extracting. Because obviously there, like everything is extremely time dependent. So we're also testing. So, but I think we just need to understand the limitations of what we're doing and have the right kinds of tests to really understand the results that we get.
Okay, Shervin, I know you can't put your hand up. You can wave and I'll try and.
Okay, but can I say something or?
Yeah, go for it.
Oh, okay. Yeah, so this was just going back. Well, actually, two things. One of them is regarding the twisting. I think already like during the Aquarius days, right? There was already like several studies actually looking at the evolution of shapes. Like there's one, for example, a famous paper by Veracero, like with who was like working with Amina about I mean, I'm not sure to what extent like this is not so common. I think it is actually fairly common that actually the shape does change as a function of radius. And then the second thing regarding to sort of using like cosmological hydrodynamical simulations, I think we could have used like cosmological hydrodynamical simulations already like 10, maybe even 20 years ago, or maybe not 20, but maybe 15 years ago. You know, like back in the day, like we already sort of learned a lot from just the fact that, you know, baryons like, you know, adiabatically contract, like for example, the inner region of the dark matter halo, and the potential becomes rounder. Yeah, and actually now we have like the tools to, you know, like for example, these basis functions that are being sort of used, but I think they haven't been as popularized as much as they should have been, right? Like I think there was already like some growing interest already 10 years ago, but it kind of like quickly faded. But I think now that like Gaia is around and that we're realizing that we're having such a hard time basically fitting and learning anything about the Milky Way, I think like these methods and tools are, you know, back on the market for people to use. And going back to these, like studying, for example, you know, globular cluster streams in cosmological halos. I mean, that's already something that was already done by somebody who quit astronomy. But Andreas Cooper actually had a very nice set of simulations where he was also looking at sort of the evolution of a couple of globular clusters. And surely, like, you know, coming back to what Azzy was suggesting, there are ways of sort of empirically, like, you know, assigning globular clusters, let's say, to dark matter particles or whatever. But you could equally think of ways of like generating these as like your Gaussian balls and throw them in simulations. So I don't think we're running out of, right? I think like we're just running out of ideas or creativity in creating like good experiments to test our methods. But I don't think we're that limited by, you know, resolution. There's always smart ways of going around it.
So there's some chat, I think, between Robin and Adrian. If you guys want to, Robin, you got your hand up.
I think we're violently agreeing, but I don't know.
Yeah, sorry about that. I had my mic off. Thanks, Shervin, for pointing people to that paper. The stuff that Andreas was doing was a good first step, but I think it's problematic that it was in dark matter only simulations, because one of the things that the other main effect of the hydro is to make the galaxy a more efficient disruptor of substructure, especially in the inner region, which is where we have all constraints. So whatever you need, whatever you want to do in lieu of a hydro simulation, for instance, if you want to explore a wider range of accretion histories than we can access with full cosmohydro zooms, is going to have to account for both the shape evolution of the potential as the galaxy forms and the depletion of subhalos over time, because the galaxy is more efficient at disrupting them than a dark matter only simulation. To Adrian's point, the overall evolution of the shape in the exterior to the part where the disk is forming is affected by things like the LMC or the SMC coming in, if you have one in your Cosmos sim, which is why I think Alex's point of whether we need to test what situations where we have the LMC in the right place and time is a good one, but it's second order to the amount that the shape evolves in the center because the galaxy is forming, is my perception from looking at this. So like in fire simulations, I have a student who's working on a paper on the shapes of those galaxies, and Nihao has done some work on that back in like 2016. There was a paper where they looked at it, and we find a lot of the same things as they did. So that's the point of the stuff that was in the chat, and I'll stop now, sorry.
Adrian, did you want to say anything?
I had a related but slightly different thought. So, but I don't want to dominate the chat, so anybody else should chime in. I feel like this keeps happening though. Oh, Anna raised her hand. There you go.
Sorry. Yeah, I wanted to ask about the kind of pick up on this discussion on the question of timescales and kind of what the streams are on sort of what type of changes in the shape are streams sensitive to, and maybe that kind of ties more also into the kinds of models we need for LMC, and in kind of which kind of streams in which part of the galaxy are affected and in what way. So I want to open that for discussion.
I was also interested in that, so I'm glad you raised that.
Sorry.
But I think even more, just to be more specific, I think there's an interesting set of theoretical questions that answer that, and there's all of the work on injecting streams into more realistic simulations and trying to understand the complex things that happen there. I think you can answer the first question, like building off of the things that you did with Hug on thinking about the information content in streams. If we go fully, non-parametric and time dependent with mass models, and then try to constrain parameters of some really flexible model, we can then specifically ask the question, what is a stream sensitive to in terms of the like 0th order parts of that thing?
So I just want to check that there's no one who wants to bring something up who isn't able to raise the hand, or maybe someone a bit more junior who would like to talk about something before, so we don't just focus on the same group of people. Is there anyone who wants to say anything? You can, I think clap might work if your raise hand feature's not, or you can try and wave if your video's on. No
also
pressure.
feel free to drop things in the chat if you don't want to speak, or put things in the Google Doc in the running notes if you want.
Okay. So Dennis, do you want to go for it?
Yeah. So I guess related to like Anna's and Adrian's questions about the kind of things that are possible. I mean, I think one thing that we see from kind of my work and Mike's work and Nico's work is that we have a Milky Way that moves in response to the LMC, and that can have effects on the stellar halo. And like Alice has recently looked at that and how it affects mass modeling in the Milky Way. I think we don't fully understand what the LMC is doing. So I think, I mean, this is probably a discussion in the other room as well about, exactly how well we have to model the LMC. I will say that for the streams we've modeled so far, like with Orphan, we were able to fit it just fine with a rigid LMC. So we don't know what kind of biases we've introduced by doing that, because obviously the LMC is disrupting. And Sophia's work has shown that for the Orphan stream, that disruption is quite important, and it's like it produces an effect which is larger than the observational uncertainties. So if we were to refit with a live model, we would have to probably get a different result. That may affect the inferred flattening of the Milky Way and how that looks like. Probably it's the same thing for Sagittarius as well, which was also fit with a rigid LMC in the same way. I think a lot of work has to be done on the modeling side in order to understand how well we're modeling, or what it takes to match what we're seeing in the Milky Way. I think that these cosmological simulations are just a great way to explore that. By putting streams into different situations in the cosmological simulations, we can really kind of see what the effects are like from let's having a big LMC in a cosmological simulation. We can see what it's doing, and we can see whether or not the tools that we're developing are good enough to explain that or not, and if they give biased results or not when we try to fit those things. So I think a lot of work is needed to be done on the modeling side. And this is also why, I think Carl Grillmeyer asked yesterday, why aren't we fitting multiple streams at the same time? And I think it's because of this fear that there's so much we don't understand right now. And there's so many subtleties going on that by combining multiple streams, you may, be kind of really biasing yourself in a very tight part of parameter space, which you're not, you're not being fair on systematics. So, yeah.
Okay, Pao?
Yeah, but I just wanted to raise a question because I want to know your opinion, but it's going to be a change of topic, so I'm happy to wait until,
Does anyone want to chime in on the subject we're just talking about before we change topic?
I vote that Stella talks about what we're doing to look at systematics to address Dennis's point.
Okay, Ting, did you want to say?
I just want to follow up on what Dennis said is, so now we are using like actual data to do simultaneous fitting to constrain Milky Way and LMC maybe simultaneously soon. But that's another thing I think would be good. So I know like there are these kind of mock data, but it would be really good if in the near future, we can have a kind of mock data that from some hydro simulation, ejecting some goblet clusters and also have certain like dwarf galaxy streams. And then we can use those kind of like mock data to see if we can recover and see the bias between the two kind of potential and the evolution versus what we recovered from that kind of mock data. So I would say that kind of tool will be very useful for this whole community, and we should really think about to have something like that. So build a mock catalog that includes something like LMC and hopefully including something like SAG, and having like all these kind of stream tracers in the simulations that we can use and mimic the thing. I don't know if how realistic it is, and I really encourage people who are doing all the fitting to fit not only on the real data but also on this mock and kind of so we can understand our systematics better.
Okay, so I think power to change topic. Rohan, were you also changing topic, or was it the same topic?
Yeah, it was a bit of changing topic, but I think we should let Stella comment now because it seems she's
Right.
doing nothing else.
Go on then, Stella.
Yeah, thanks. I heard Robin call out to me before. I guess you meant about the work we're doing currently with the fire simulations?
Yeah.
Okay. So yeah, I've been recently looking at some of the streams from dwarf galaxy origin in the fire simulation, and so using these like large streams in combination with the action clustering method that I talked about in this conference as well, and also looking at just different sections of these streams. So basically just chopping them up and seeing what happens if I use just the apocenter location in this clustering algorithm, or using just pericenter location or the intermediates, and then kind of starting to combine them together to see which of the two would give the best estimate for us. And I'm kind of still halfway through this work, but it seems to be that it's still true that you need streams from just different galactocentric distances, and that's what gives you the best results. And if you look really at the particular parts of the orbit that they're on, so following the loops through, I think it's too early for me to comment on the fact, but our assumption is that possibly having like combinations of pericenter and apocenter would give the best options, best results here. I don't know, Robin, you meant me to comment on anything else in particular?
No, that was it. I'm just the situation, at least in our method, with understanding the concern that Dennis has, which is a valid one, is a little bit helped by the fact that you can kind of see when you fit simultaneously lots of streams where exactly the model isn't flexible enough, because that will be the region of your multidimensional parameter space where you have the most tension between your different streams. And I think given the quality of the measurements these days, that's usually from our experiments more ascribable to systematics due to your model being not flexible rather than problems with your actual data.
Okay, so we have 5 minutes. Pao, do you want to jump in now?
Yeah, so I mean, I was just wondering, going back to the conceptuals, right? You said, what do we want to learn? I guess I was wondering if the distribution, the statistical distribution of the streams, like their kinetic temperature, their widths, their lengths, number of streams, if this changes from different cosmology, from cosmology to cosmology, because I would understand that there should be a correlation with the mass of the objects that, so the mass distribution of the satellites, but then again, you have other effects that can increase the kinetic temperature, for instance. And and if this could be a discriminant or not. I would be interested in knowing your opinion. Just
Someone want to jump in on this? Sarah's your hand up about this.
Yeah, I just wanted to say, I think that's one of the things that would also be interesting to do for all the sample of external galaxies that we have with known streams. If you really want to start comparing the width and number of streams and how many you see at present day, comparing to cosmological expectations, I think really using all the external stream information that we have would probably be helpful there too.
Okay, Rohan, thanks for your patience.
No problem at all. I was going to suggest something that was a bit related to the more like, how do we get to more realistic modeling of streams, but it was also a bit of a topic change in the sense that I was curious about people's opinions about how we incorporate information about the dwarf galaxy hosts of the globular clusters that are now being disrupted into streams in the Milky Way, right? So like we think that a lot of these streams seem to cluster in orbital quantities and seem to like be associated with mergers like Sagittarius or the Gaia Sausage and Enceladus event and so on and so forth, right? And we have a lot of information about these events, right? So we know, for example, when Sagittarius entered the galaxy, when GSE entered the galaxy. So how do we like propagate that information into our modeling of streams, into our interpreting like the gaps or various features, right? So just as a rough example, stream from a globular cluster associated with an accretion event that happened at like redshift 2-ish versus one that is much more recent, right? For example, I think like the Cetus related streams are much more recent compared to like the ones that might be associated with GSE. How do we like incorporate that information into our modeling, into our thinking, into our simulations is an issue I wanted to bring up in general.
Thanks, that's a great point. I think the coupling of this modeling and the assembly history, given that we now know we have to care about the LMC, I feel like now we can't do these things distinctly. Like we kind of, you either do one or the other, used to be anyway, that you're measuring the potential or some parameter, or you want to know the assembly history. But now we probably, it has to be jointly, that these things are affecting each other. I think it's a great point. Okay, the last couple of minutes, Nyash. Did I nail it that time?
Yeah, sure. So I just wanted to add that this issue of identifying streams, and I'm not sure exactly who commented on this, but so I mean, of course, there could be many streams out there that we cannot identify just because we don't have enough data. But I mean, just there's an analogy with cosmology where you have galaxy clusters and you have clustering of galaxies. And most galaxies are not actually in galaxy clusters, but you can still use their clustering to learn about lots of things. And I guess I was just going to say that, yeah, so by just focusing on the streams, we're limiting the information. There is much more information about the Milky Way halo that we could learn by clustering, which I think some of us, have advocated for. But just this issue of limiting yourself to streams limits the information you can gather. There could be things that have nothing to do with the streams, but nevertheless, they are clustered in the action space just because of the hierarchical structure formation. And yeah, I was just saying there's just much more to be learned there.
Okay, given that there's a countdown going and I feel like people shouldn't talk under pressure because this is too much pressure in for me and I'm trying to just stop this discussion. Thank you all for the great discussion. That was great. Thanks a lot.
Thank you.
Thanks, Alice.
Yes, so let's go ahead. I mean, we'll just totally open up the floor as far as I'm concerned for reporting from either room key issues that people identified. Please, of course, raise your hand. We'll call on you. Dennis, go ahead.
I guess one issue that we raised a lot and talked about a lot in our room was about the need to kind of understand what we're really measuring when we measure things with streams or with actions or with anything. We're saying, you know, that kind of the need for cosmological simulations with realistic mocks. And so we can apply our testing, kind of our fitting techniques on those and see what we're actually measuring and if our tools are good enough to actually measure that. And similarly, you know, with the effect of the LMC on the Milky Way, you know, using n-body simulations with disrupting LMCs and Milky Ways, and then testing what we're actually measuring when we fit a stream in that, let's say with a rigid potential for the Milky Way and the LMC, just to understand, you know, what kind of advances in the models that we need in order to fit those things, what we're actually fitting in these time-dependent and kind of changing potentials.
Sarah, go ahead.
Yeah, and then I was also in group 1. We also just summarized a few things that have been discussed in the breakout rooms of how at redshift 0, we could still have, even in a dark matter only simulation, you could have a varying dark matter shape as you go out in galactocentric radius. And then introducing baryons will spherulize the central parts a bit. And then besides just the changing shape with where you're located in the galaxy, of course, it also comes in with time. So obviously, if you look at fire, there will be a big change to the potential when the disks are actually forming. And then as Dennis just said, also with the infall of the LMC. So we're just kind of overall discussing all these different aspects of baryons and changing shape with radius and also in time, and how we'll really need to do a lot of efforts on the modeling side to learn all of these things with streams.
Can I ask if group 1 came up with any solutions for what we need for modeling? Room 2 didn't come to conclusions either. So, okay, all right.
I just want to remind everyone, the goal of this meeting is not to solve all of astronomy. It's to have these discussions. So we can continue to have these discussions beyond the meeting and hopefully then figure it out over the next few years.
But if we did, would that be so bad? Sorry, let's, Dennis, is your hand up again, or is this, I'm not sure. I lost track.
Yes, it's up. Yeah,
okay,
yeah,
go ahead, Dennis.
I guess you asked if we had any solutions. So I guess one of the things we discussed was the kind of slight limitations of cosmological simulations when looking at streams. So there's a recent paper by Neil Bannock and Joe Bovey on what happens when you have the particle resolution and how that affects streams. They showed that these, you know, just the particle resolution of a dark matter only simulation will heat up a globular cluster stream. And so we kind of discussed that, you know, there could be some biases then if you were to definitely if you take globular cluster streams from cosmological simulations, and then perhaps even dwarf galaxy streams, probably slightly affected by that heating. So we said, you know, one, the having basis function expansions fit to cosmological simulations. And so Jason Sanders had people like that recently. And then we were, like Sarah Pearson was saying, how we need to include the baryons as well in that. So right now those fits were done for dark matter only simulations, but now we're currently working on doing it for hydrosims as well in order to have these realistic potentials. So then, you know, disrupting and then fitting streams, those potentials would be a start to answering some of the questions that we raised. But obviously it's not the full solution, it's just part of the solution.
Marius?
Yeah, I think there are many challenges when it comes to having cosmological simulations that resemble the Milky Way. Also because we are still uncertain about the galaxy formation physics. So for example, the satellites galaxies that we get may not resemble as closely as possible the observed properties, and then the disruption, also maybe the structure of the stellar disk. So again, you know, like we have to be careful how we interpret those cosmological simulations. So maybe at least for the current time, having this kind of constrained simulations that try to reproduce the Milky Way as much as possible, it's the better choice for the short term. But yeah, ideally in the long term, that's really what we want, is really cosmological simulations.
I feel like we convinced you to go for the constrained ones during our chat, so that's great. I'm going to go to Monica.
So I'm sorry, I missed much of this because I was teaching, so I only got the last few minutes of one of the discussions. But and therefore, since I didn't hear anything about what was happening, I just want to sort of maybe play devil's advocate and say, you know, I feel like we can all work really hard and come up with really complicated models with very high resolution and all these things. But I think it's worthwhile stepping back and asking, what are the questions we still want to ask, right? In Binney and Tremaine, we had really nice equilibrium models. We could write things down, if not analytically, you could do them, numerically, gave you great insights. Gave you insights about the physics that was going in, maybe helped you understand cosmology, maybe understand dark matter, galaxy formation. And I feel like now we've got to a stage where everything is so complicated that, maybe we'll be able to explain, 5 streams beautifully, but what do we want to learn from this? And so I feel like rather than saying, how complicated can we make the models, maybe we think and say, what is it that we still want to really learn about galaxy, dark matter, galaxy assembly, or maybe even star clusters that we don't know, and what's the best sort of way to, use our time rather than just going for, much more complicated simulations. So I'm going to stop. That was just my sort of a soapbox moment, but I'll, if it's off tangent, then I won't, then that's fine.
No, that was much needed, and it reminded me that I meant to bring back our science slides at the end to see how we were doing on the big questions that we identified at the beginning. So thank you very much for that statement. Robin, I think you had your hand up. Have your hand up.
Thanks. I just wanted to push on something that both Marius and Monica brought up. I think that there's a need for the kind of simulations that we're doing, even in the face of combating our ability to represent all the physical processes that are going on. Because for one, we are starting to have some convergence. And for two, I think it's the only way to explore the space, because we don't know, for instance, the Milky Way accretion history perfectly, the space of uncertainties and biases that cosmology is going to program in at some level. I don't think that a cosmological simulation is always what you need, but I do think you need to be aware of the cosmological context at this point all the time, because it's clear that that's having present day effects on the situation that we're trying to model. And at the same time, I think that's how you're going to tell how simple of a model you can get away with that is still telling you something that you want to know about the galaxy. And so I actually agree with you, Monica, that we've basically already made the most complicated models of the Milky Way that we can, which are these giant zoomed simulations that either are constrained to look like the Milky Way in some way, or are just sampling what we think the Milky Way's mass tells us about that. But what we're going to actually learn is going to be quantified in fewer numbers than a couple of billion particles. And so understanding what those numbers are and how they're meaningful is, I think, the real reason why we need to test models against those. Oh, that's not what I wanted to do.
Sorry, testing models, can I just ask a clarification? So testing models against cosmological simulations or against scenarios? Okay.
Yeah, and I think there's definitely a place for both purely cosmological initial conditions and the kind of constrained stuff and tuned models that are meant to represent the Milky Way in ways that we can't get easily from the cosmological context. You need all of those resources to stress test the models that you're trying to build.
I think that's a great point. I want to come to Adrian first to bring up, I think, a big point, and then Marius.
Yeah, I just put something in the chat. Monica, thank you for bringing that up. I think that was obviously our intent, is to return to these big things, and sometimes that gets lost when you get into discussions that go off into details. But I think the way I perceive these discussions is not, let's build the most complex model of the Milky Way so we have a complex model of the Milky Way. It's, we need to be able to build in the relevant complexities so that we get unbiased constraints on a set of things that we think are important. And so it's those things that I think we should all write down. I have a list of things that I think are important. I'll make a section in the running notes, and I think we should just start dumping in what we think are the key, like the things that we want unbiased measurements of that we think connect to fundamental physics or fundamental astrophysics. Like these are the things that will be in the next Binney and Tremaine, I think, that future us will call beautiful things, right? But yeah, I just want to emphasize, like, I think all of this discussion has been great, and it's important to keep this context in mind. We're not trying to build this model of the Milky Way just so we can show it to people and say, look at how well we reproduce the Milky Way. There is an underlying context.
Thank you. Yes, Marius, please.
I just wanted to emphasize the need for tests. So actually, Simone Biver in our group actually made this very good suggestion that the more I think about it, the more I like it, to have this kind of blind mocks, maybe with different complexity. And then we should actually try and, test as many methods as possible and maybe identify the most promising one, though, the ones that give enough flexibility such that you get unbiased results. And maybe one of the next meetings or workshop that we organize, that may be actually one idea to try and organize a workshop in which the community can come together, maybe discuss some potential mocks, how to create them, and actually apply the tools to them.
Rodrigo.
Yeah, so I just wanted to bring up a point. I completely agree with what has been said before. But I work in a department where there are people who are interested in, other ideas about gravity. And I don't think I can put my hand on my heart and say that of all of the systems that we've observed to date, in fact, I don't think there's a single one that has been modeled so that I think it's, its chi-squared is sufficiently small that I say it's fine. And it's quite possible that there's interesting things that are hiding there that are actually pointing towards, completely different pictures. So I just wanted to put that out there as well.
Do you have any, I'm going to put you on the spot for a second. Do you have any proposals for things that we can look at to test? Or?
Well, to be honest, that's precisely the reason that we tried developing that software that was presented in this talk I gave today. And the idea was to have a sort of, a diagnostic means of figuring out what the acceleration field of the galaxy was. So, I mean, that's one possibility, and there are hundreds of others, no doubt.
Great, thank you. I think Guillaume had a follow-up on that. Go ahead, Guillaume.
Yeah, so just to complete about what said Rodrigo, yeah, we can look for that with globular cluster streams, for example, run globular clusters, run the LMC, things like that. I mean, like one of the things I think is really important for the next 5 years, and it's really what I would like to do, is to really be sure that we can detect the dynamical friction tail beyond the LMC, for example, to prove that dynamical friction at the scale of the galaxy exists. So it's basically proving that dark matter exists, and so it's rule out some modification of the gravity or things like that at galactic scale, which still have to be proven for that. Where is there the strength of them? So I think that doing that is one of the main goals for that. Well, that is from my point of view again.
Great ideas. There's a discussion happening in the chat right now that I'm not entirely following because I was listening there. So I was wondering if Robin or Eugene could summarize what's being said.
I think it's for the fifth day. We probably should have a discussion there about the mocks and the community efforts of testing and comparing methods.
Okay.
Yeah, I think if we were to revisit what we learned from the efforts to do the Gaia challenge, now that a lot of people's models have evolved, it would be an interesting point.
Martin.
Hi, hello, it's my turn. Okay, sorry, fast. I just wanted to say if we should, as a community, get involved in measuring the velocity of the sun in the galaxy, and if, because that may introduce biases in all the models fitting. Thank you very much.
Yes, we'll see if there's a follow-up to that. I want to go to Adrian and for maybe something big, and then we'll come back.
Well, if anyone wants to comment on that, please do. Yeah, I was gonna say some broad things and slightly change the topic, so I'll pause for a sec.
Dennis, are you a comment on that?
Yes, I am. I guess
Go ahead,
I wanted to raise the point, yeah, that I mean, I think that the sun's velocity is already quite well measured, given kind of gravity's distance measurements to the galactic center, plus the proper motion measurements of Sag-A star. And I think, you know, one issue with the motion of the sun is that, you know, the whole Milky Way is moving now in response to the LMC. So like Mike has shown, and like some of my work has shown, and Eugene's work has shown, you know, the Milky Way is moving by about 30 or 40 kilometers a second. And so depending how you're measuring the motion of the sun, depending like how far out your tracers are, you may get a biased result. And so for example, like if you use the stellar halo at 50 kiloparsecs and say that it shouldn't be moving, and you measure the sun's velocity that way, like you will get a crazy, you know, vertical velocity for the sun. And if you measure it locally, you get a different result. So I think we need to understand what the motion of the sun really means and like what it's relative to. And that there's a region in the inner Milky Way where that's like a well-behaved thing, but then beyond that, you know, the Milky Way is deforming and like really out of equilibrium. So I guess I wanted to argue that I think we already know the sun's position relatively well compared to what we need for potential modeling, given the other kind of problems we're facing.
Thank you. Yes, good point. Back to Adrian.
I just wanted to raise Monica's comments. I loved, and they triggered all kinds of like thoughts that I've had over the years about the streams community and our like subfield and how it connects to other fields in astronomy. And I don't have anything specific, any conclusions, just things that I think would be good to remember and to think about, which is like the difference between our field and studies of the Milky Way and cosmology or certain exoplanet subfields, in that cosmologists will do a survey because they know exactly what they want to measure and they know exactly how they're going to do it. And so a lot of times people in departments I've been in will say like, well, Gaia released their data, you know, what are the Oort constants? What's the, like, tell me the dark matter force at the solar neighborhood. And like, I then have to remind them that like, that's not the point of Gaia at some level. Like the point of Gaia is that we're still learning a lot about the Milky Way and its evolution, and it's a very complicated place. And all of that is useful information to learn, and we're still working out what to measure, and that's okay. Like, I just want to say that it's okay that we're still working on all of these things, but I think we need to remind people of this, that it's not like Gaia releases data and we can compute things and deliver like immediate results that we can distribute to the broader community. And so I think that puts us in a unique place to keep in mind.
So is that arguing for like the longer, like pick the longer horizon that we're thinking about right now?
I'm not sure what I'm arguing for, other than to say that yeah, I guess we need to be a little bit strong. Like we need a lot of times when I give a talk and I talk about details of something, people say, well, the Milky Way is just one galaxy. Is it really interesting? You know, like to learn that about the Milky Way, and we'll have like retorts about certain aspects. And I think we need to be stronger as a field about pushing back and saying like, look, we're working on this. It's a really complicated thing. And you know, like we don't have two numbers that we can measure from all of this data. We still don't know what that is. So it's more of like a perception and how we present ourselves to other people.
That's great. Thank you. Yeah. Maybe we can figure out what those numbers are for us. No. Niesh and then Ting.
So as someone who's worked on cosmology, probably more than galactic dynamics, I guess it's a little bit offensive to say that cosmology is just about two numbers. And maybe 50 years ago, that was the case. But yeah, I mean, I think basically that both communities have something to learn from each other, both cosmology and I think dynamics community. And I think what's maybe something to learn is that, but I mean, I think in some sense we are lucky in cosmology that there is this cosmological principle that hasn't been too seriously challenged. I mean, we are a typical place in the universe, and the universe is statistically homogeneous and isotropic. And unfortunately or fortunately, the same cannot be said about the Milky Way. So that kind of limits some of the options. But I mean, I think there are still things to be learned, and in particular, the statistical correlations, so this is kind of something I brought up in the last breakout room. We can talk about so there are galaxy clusters and galaxy clustering in cosmology. And streams are like galaxy clusters in the sense that they're clusters in the space of integrals of motion, but galaxy clustering is a much richer field than galaxy clusters because most galaxies are not in galaxy clusters, but they're all clustered as far as we know. And so there's a lot of information to be learned there if you can just dig it properly. And maybe you could use similar techniques like correlation functions or power spectra that are used in cosmology. Now, it may not be two numbers. There are many more numbers. I bet in cosmology there are many more numbers that are to be learned. But I think it's the question, of course, is can we use all the information properly? Like, for example, clustering in various spaces as a function of separation, and translate it to the best information we're interested in learning. Anyway, so that was my rant.
It was a good rant, thank you. Ting, and then I'm going to bring back the slides from the intro to look at the questions that we asked. Go ahead, Ting.
Okay, I just want to follow up on what Adrian's talking about. So, because I'm an observer, astronomer, working in Milky Way, but I kind of like start my career path in a lot of these, how do you say, the dark energy kind of, or like a high energy kind of those experiments. So when Adrian talking about this, I was thinking about maybe that's something we should think about, and maybe it's more for Friday topic, but we should kind of think about this. So for as Adrian said, for those people who are working on cosmology, they ask like what the question they want to ask, and then they propose an experiment to test that. And then they have a group of people to do that, starting from simulation. So there's a group of people doing all the simulations, working on data challenges, and then have all the reduction, and then try to answer the questions. Well, we are in a way of like, oh, here is the Gaia data. They are great. What kind of question I can answer? I answer question A, question B, and that was like three people working on it. It's kind of the astronomer style versus high energy particle physics style, I would say original. But we should think of a way as a community here, and we have the group here. I think people are talking about, like, say, dark matter, when a lot of these particle physics are super interested in constraints from the astrophysical probes to constrain dark matter. So we also should think of a way, like, what are the questions we think we can answer? And to answer those, what is the experiment we should design? And not just getting the data, but also working on simulation and working as a group and put this kind of community effort. I think this is a great platform to think about that and initiate that. And I'm not saying that's a better way than our traditional astronomer way, but I really think this is the opportunity for us to think about a different way and to make stellar streams and like galactic halos as a probe to constrain those. We have the interest scientifically for those high energy or particle physicists or funding agency to support us. I think we have that kind of science motivation. We also have the group of people to formally manage those, so that we have a group, a collaboration that has theorist, simulator, and observer and data people all putting together. And really, that's kind of a direction and angle we should think about, instead of like having small groups is great, but we should think about also merging and expand as we are one group and talking to the other groups. Sorry, it took maybe too long.
No, that was great. So our exercise is to herd cats here, I think.
I just wanted to respond in one second and just say I did not mean any ill wills towards cosmology. I didn't mean to say two parameters in a pejorative way. I meant to say it as like, that's what we could have. Like, it's a good thing that they have worked to figure out what are a small set of parameters that they can measure really precisely. And that's something we could do as a community.
Yes, so maybe in the spirit of trying to answer what those two parameters are in the last 2 minutes, I just want to see where we ended up for the main science questions that we laid out at the very beginning, because maybe these are things that are driving it. Ting's points and Adrian's points and Yanish's points and Monica's points and everyone else's points that were made today. So the three big science questions that we proposed, at least for start today, about the mass, shape, concentration of the galactic potential, important constraints on dark matter models, and the connections to the small scale problems. Is there anything else from the big science questions from today to add to this maybe, and how they connected to all of the talks?
I think one question that was consistently popping up was, how unique is the Milky Way? How much does it tell us about galaxies in general?
I think I think that's a really good question. I figured out how to see hands raised. So if anyone has a last minute, I guess we're literally in the last minute. Any last minute thoughts here? Okay, well, these are our big science questions. We can obviously add to this or comment on them later, but I'll throw back to the organizers, I guess, to do the full day wrap here, maybe.
I think this is it. I guess there's like one topic that was really different that was brought up by Rodrigo and Alex, saying that maybe we need to kind of generalize like the second point about what can we learn about dark matter. Maybe we can make it just more general, like what can we learn about the gravitational field of the galaxy, so that captures both the modified gravity and the different dark matter models. But I think, yeah, that was good discussion. I think we also got a number of sort of suggestions for kind of steps forward, which we can discuss on Friday in more detail. So thank you everyone for tuning in today. We will send like the recap email with the recordings a bit later once we close on the Zoom account and save this to the cloud. Thank you so much for participating. Please continue all of these conversations on Slack. And if I'm not forgetting anything else that my SOC members like think of in the next 5 seconds, we'll see you tomorrow, same time. Bye. And of course, sorry.
Thank you.
One thing we forgot. Thank you to our moderators.
Thank you. Yes, you did a great job, an amazing job.
Yep. Thank you, moderators.